High-impedance grounding systems are a perfect candidate for processes where limiting fault current is crucial. High-impedance grounding systems limit the amount of fault current that can flow in the event of a ground fault. This prevents damage to equipment and buildings. A ground fault occurring while working on electrical equipment could be limited by a high-impedance grounding system. The fault current is reduced, preventing main service ground fault protection equipment from tripping and avoiding building shutdowns or fires. The advantages of using a high-impedance grounding system in applications: firstly, it limits fault current. High-impedance grounding systems limit the amount of fault current that can flow, reducing the risk of damage to equipment and buildings. Secondly, it prevents nuisance tripping. High-impedance grounding systems could help to prevent nuisance tripping of circuit breakers and other protective devices. This can improve productivity and reduce downtime. Thirdly, it protects equipment. High-impedance grounding systems can help to protect sensitive electrical equipment from damage caused by ground faults. Fourthly, it improves safety. High-impedance grounding systems can help to improve safety by reducing the risk of electrical shock and fires. In addition to these benefits, high-impedance grounding systems are also relatively easy to install and maintain, making them a cost-effective solution for protecting electrical systems in industrial and commercial applications. Here are some of the precautions that should be taken when using a high-impedance grounding system. Firstly, properly ground all equipment. It is important to ensure that all electrical equipment is properly grounded to prevent the accumulation of static electricity and to provide a path for fault current to flow. Secondly, use surge protection devices. Surge protection devices can help to protect electrical equipment from damage caused by voltage surges. Thirdly, maintain the grounding system regularly. Regular maintenance of the grounding system is very important to ensure proper operation. This includes checking grounding connections, testing grounding impedance, and recording maintenance records. By following these precautions, a high-impedance grounding system can be safe and effective. To elaborate, a high-impedance grounding system employs an impedance, typically a resistor, between the system neutral point and ground. This impedance limits the ground fault current to a low level, typically 5 to 10 amps. This is in contrast to solidly grounded systems where ground fault current can reach thousands of amps. The limited fault current in a high-impedance grounded system offers several advantages. Firstly, reduced equipment damage. The lower fault current minimizes the stress on electrical equipment during a ground fault. This reduces the likelihood of damage to conductors, transformers, and other components. Secondly, decreased arc flash hazard. Arc flash is a dangerous phenomenon that can occur during electrical faults. The severity of an arc flash is directly related to the magnitude of the fault current. By limiting the fault current, high-impedance grounding systems significantly reduce the arc flash hazard, improving safety for personnel. Thirdly, improved system reliability. High-impedance grounding systems can allow for continued operation during a ground fault. Because the fault current is limited, the system can often continue to operate without tripping a circuit breaker. This can be crucial in applications where downtime is unacceptable. Fourthly, reduce transient overvoltages. High-impedance grounding systems can help to dampen transient overvoltages that can occur during switching operations or lightning strikes. These overvoltages can damage sensitive electronic equipment. The installation of a high-impedance grounding system involves several key components. Firstly, a neutral grounding resistor or reactor. This is the heart of the system. It is a resistor or reactor that is connected between the system neutral point and ground. The resistor or reactor is sized to limit the ground fault current to the desired level. Secondly, a neutral grounding conductor. This conductor connects the system neutral point to the neutral grounding resistor or reactor. It must be sized to carry the full ground fault current. Thirdly, a ground fault relay. This relay is used to detect ground faults. When a ground fault is detected, the relay can trip a circuit breaker or sound an alarm. Fourthly, a ground fault monitor. This device continuously monitors the ground fault current. It can be used to detect developing ground faults before they cause a major problem. The design of a high-impedance grounding system requires careful consideration of several factors, one being system voltage. The system voltage determines the size and rating of the neutral grounding resistor or reactor. Another factor is the fault current limit. The fault current limit should be selected to minimize equipment damage and arc flash hazard while still allowing for continued operation during a ground fault. Yet another factor is the coordination with protective devices. The high-impedance grounding system must be coordinated with other protective devices in the system to ensure the ground faults are cleared quickly and safely. Maintenance of a high-impedance grounding system is essential to ensure its continued effectiveness. Routine maintenance should include, firstly, inspection of the neutral grounding resistor or reactor. The resistor or reactor should be inspected for signs of damage or overheating. Secondly, testing of the ground fault relay. The ground fault relay should be tested regularly to ensure that it is operating properly. Thirdly, testing of the ground fault monitor. The ground fault monitor should be tested regularly to ensure that it is accurately measuring the ground fault current. Some common applications for high-impedance grounding systems are, firstly, industrial plants. High-impedance grounding systems are often used in industrial plants to protect equipment and improve safety. Secondly, data centers. High-impedance grounding systems are used in data centers to prevent downtime caused by ground faults. Thirdly, hospitals. High-impedance grounding systems are used at hospitals to protect sensitive medical equipment. Fourthly, wastewater treatment plants. High-impedance grounding systems are used in wastewater treatment plants to protect equipment from corrosion. While high-impedance grounding offers numerous benefits, there are also some potential drawbacks. Firstly, increased voltage to ground. During a ground fault, the voltage to ground and the unfaulted phases will increase. This can be a concern in systems with sensitive electronic equipment. Secondly, difficulty in locating ground faults. Because the fault current is limited, it can be difficult to locate ground faults in a high-impedance grounded system. Specialized equipment may be required to pinpoint the fault location. Thirdly, potential for ferroresonance. Ferroresonance is a phenomenon that can occur in high-impedance grounded systems under certain conditions. It can lead to overvoltages and equipment damage. Proper system design and grounding practices can mitigate the risk of ferroresonance. Regarding the NEC, the National Electrical Code, Article 250.36 covers high-impedance grounding. This section provides requirements for the installation and grounding of high-impedance grounded systems. It addresses issues such as conductor sizing, overcurrent protection, and ground fault detection. It's important to consult the latest version of the NEC and relevant product standards for specific requirements and guidelines. In addition to the resistor, reactors can be used as the impedance element in high-impedance grounding systems. Reactors, also known as inductors, offer some advantages over resistors, especially in systems where transient overvoltages are a concern. Reactors introduce a higher impedance to high-frequency currents, providing better damping of transient overvoltages caused by switching operations or lightning strikes. This can help protect sensitive electronic equipment from damage. However, reactors are generally more expensive and larger than resistors. A choice between a resistor and a reactor depends on the specific application and the relative importance of transient overvoltage protection. Another consideration is the type of ground fault relay used. There are two main types of ground fault relays. Firstly, zero-sequence relays. These relays detect ground faults by measuring the zero-sequence current, which is the current that flows in the grounding conductor during a ground fault. Secondly, residual voltage relays. These relays detect ground faults by measuring the voltage between the system neutral point and ground. Zero-sequence relays are generally more sensitive and faster than residual voltage relays. They are also less susceptible to nuisance tripping caused by unbalanced loads. However, zero-sequence relays require a dedicated zero-sequence current transformer, which can add to the cost of the system. Residual voltage relays are simpler and less expensive, but they may not be suitable for all applications. The choice of ground fault relay depends on the sensitivity and speed requirements of the application. Furthermore, it's vital to remember the importance of proper grounding practices throughout the electrical system. All electrical equipment must be properly grounded to provide a low impedance path for fault current flow. This includes grounding the equipment enclosures, raceways, and cable shields. Proper grounding helps to minimize the voltage rise on equipment enclosures during a ground fault, reducing the risk of electric shock. It also helps to ensure that ground fault protective devices operate quickly and reliably. Grounding electrodes, such as ground rods and ground plates, must be properly installed and connected to the grounding system. The grounding electrode system should be tested regularly to ensure that it is providing a low impedance path to ground. In addition to the NEC, other standards and guidelines may be relevant to the design and installation of high-impedance grounding systems. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA. IEE Standard 142, also known as the Green Book, provides recommended practices for grounding of industrial and commercial power systems. NEMA standards provide guidance on the design, testing, and application of electrical equipment, including grounding equipment. Consulting these standards and guidelines can help ensure that the high-impedance grounding system is designed and installed in accordance with best practices. When a ground fault occurs in a high-impedance grounded system, the voltage to ground and unfaulted phases will rise. The magnitude of this voltage rise depends on the system voltage, the impedance of the neutral grounding resistor or reactor, and the location of the fault. In a three-phase, 4-wire system, the voltage to ground and the unfaulted phases will rise to approximately 1.732 times the normal voltage to ground. For example, in a 480/277 volt system, the voltage to ground and the unfaulted phases will rise to approximately 480 volts during a ground fault. This voltage rise can be a concern in systems with sensitive electronic equipment. Surge protection devices, SPDs, should be installed to protect equipment from transient overvoltages. SPD can help to limit the voltage rise during a ground fault, preventing damage to equipment. The location of ground faults in high-impedance grounded systems can be challenging due to the limited fault current. Traditional methods of fault location, such as using a clamp on ammeter to trace the fault current, may not be effective. Specialized equipment, such as ground fault tracers, may be required to pinpoint the fault location. Ground fault tracers inject a high-frequency signal into the grounding system and then use a receiver to detect the signal. The signal is strongest at the location of the ground fault. This process allows the technician to accurately locate the fault. It's also important to remember that high-impedance grounding is not a substitute for other safety practices. Electrical safety training, proper lockout/tagout procedures, and the use of personal protective equipment, PPE, are essential for preventing electrical accidents. High-impedance grounding is just one layer of protection in a comprehensive electrical safety program. In summary, high-impedance grounding systems offer a number of benefits for protecting electrical equipment and improving safety. They limit fault current, reduce arc flash hazard, improve system reliability, and dampen transient overvoltages. However, they also have some potential drawbacks, such as increased voltage to ground and difficulty in locating ground faults. Proper system design, installation, and maintenance are essential for ensuring that high-impedance grounding systems operate effectively. Consulting relevant standards and guidelines, such as the NEC and IEE standards, can help ensure that the system is designed and installed in accordance with best practices. Additionally, it is good practice to consult with a qualified electrical engineer when designing and installing a high-impedance grounding system. An electrical engineer can help to assess the specific needs of the application and select the appropriate grounding system. They can also provide guidance on system design, installation, and maintenance. Regular inspection and maintenance of the high-impedance grounding system are essential for ensuring its continued effectiveness. This includes inspecting the neutral grounding resistor or reactor, testing the ground fault relay, and testing the ground fault monitor. Any problems that are identified during inspection or testing should be corrected promptly. If there is a ground fault, the system should be inspected and tested to ensure that it is operating properly and there is no other electrical issues that could be the root cause.